Hi, I am Laiping Zhao. I'm from Tianjin University. I would like to share our work on Rhythm, component-distinguishable workload deployment in Datacenters. This is the outline. In this presentation, we will discuss the problem of low resource utilization in data centers. This figure shows an example from Aliyun. The average CPU utilization of co-located cluster in Aliyun approaches to 40%, according to their recent trace. 40% is an improved, but still very low utilization. Co-location has been proved to be an effective way to improve the resource utilization. However, the interference among workloads causes unpredictable latency. Previous work solved this problem using two common approaches. The first one is profiling-based approach. It relies on a special profiling phase. We can know the characteristics of each workload. Then we can schedule them in a cross-complementing way. It can generate very high throughput, but also it yield very high cost. A second approach is a feedback-based approach. It doesn't have the profiling phase, but directly deploys the workloads in the machine, but passively adjusts the resource allocated to each workload during the runtime. The many component services are very common in data centers today. And we just show two examples. First one is from Datacenters. It is a social network service, and it consists of 31 microservices. A second example from Google. A single transaction in Google can across 40 racks of 60 servers each. There is still an open problem here. That is, how can we feedback control when a request is served by multiple components collaboratively? Given an overall latency requirements, it is easy to derive a sub-latency requirement for each component. But it is difficult to derive a sub-tail latency requirement if we are given an overall tail latency requirement. That is, we do not know how the component level control can affect the overall tail latency. We evaluate how the interference on each service component can affect the overall tail latency using two examples. The first one is the fan-out Redis. We've observed that the master component in Redis is always more sensitive to the interference than the slave component. It can generate much higher impact on the 99th percentile latency. The second example is for the multi-tier e-commerce website. In most of the cases, MySQL component is more sensitive than the Tomcat, except in case of the DVFS interference. The differences between components can achieve as much as 435% and the same source of interference. Given these observations, we design our system Rhythm. Its insight is components with smaller contributions to the tail latency can be co-located with small BE jobs. There are two challenging issues towards this problem. First one is how to quantify the contributions of a component. A second challenge is how to control the BE deployment aggressively, including when to co-locate and how many BEs can we co-locate with an LC component. To quantify the contribution of each component, we need to know which component has been used to process a user's request. So the first step is to track the user's request. We describe the call path of a user's request using a causal path graph. This graph is built using the send and receiving events in the system, including its accept event, receive, send, and close event. Each event is defined using 4 elements, like including the type, timestamp, context identifier, message identifier. The context identifier is used to find the connection between two events in the same host for the same request. And message identifier is used to find the connections between two different hosts, but for the same request. So context identifier is defined using host IP, program name, process ID, thread ID, and message identifier is defined as send IP, sender's port number, receive IP, receiver's port number, and message size. Because multiple components can be scheduled in the same server, but the co-location is decided based on the server level. So we define a new abstraction, server pod. It is a collection of service components on the same physical machine. For each server pod, we derive a contribution to the overall tail latency. The different server pods could have different contributions. Our current definition of contribution is simple. Server pods with higher average sojourn time, higher sojourn time variance, and higher correlation with the tail latency contribute more to the tail latency. So we define the contribution as a multiplication of the 3 parameters. The question is this definition effective? We evaluate the relationship between a server pod sensitivity and the values of its contributions. For sensitivity, we use the metric is the increase in the 99th percentile latency when a single server pod is interfered by different bees. For example, this figure shows the 4 server pods from the e-commerce website when they are interfered by different bees. We find that the contribution values derived by our definition is almost linearly correlated with the server pod sensitivity. So we use the current definition of the contributions. Given the different contributions of the server pods, now we can decide how to collocate the B jobs with LC service. A server pod with a larger contribution to the tail latency can only be collocated with a small number of B jobs. We make this decision using 2 thresholds. First one is the low limit. It allows the collocation when request load is less than low limit. The second threshold is the slack limit. It is a lower bound of slack for allowing the growth of B. The low limit is used to decide when can we collocate workloads. Each server pod has a low limit. It is derived using the knee point in this figure. This figure describes how the coefficient or variance of response time varies over different loads. We can see there is a very special point. We call it knee point. After the knee point, the COV increased significantly, meaning very unstable performance. But before this point, stable performance. So we allow co-location only before this point. And the low limit for the MySQL is 76% of max load. In case of the Tomcat, it is 87% of the max load. The slack limit is used to decide how many bees can we collocate with an LC service. It is initialized with 1, but get updated in iterations until we find the maximum value but still guarantee the SLE. A server pod has a larger contribution to the tail latency will have a smaller slack limit. The second server pod that has a smaller contribution to the overall tail latency will have a larger slack limit. We monitor the slack, which is the difference between the tail latency in SLA and the current tail latency. If it is less than 0, we stop BE because SLA already violated. If it is larger than 0, but less than half of the slack limit, we cut the resources allocated to BE. If the slack is larger than half a slack limit, but less than slack limit, we only disallow the growth of BE. Otherwise, we allow the BE growth. We evaluate the performance of Rhythm using several benchmarks, including both LC services and BE jobs. We deploy them in a test bed with 16 sockets, and the configurations of the sockets are listed here. We compare Rhythm with another approach, Heracles. We can improve the EMU, that is the LC throughput and the B throughput, by at least 11% and at most 24% in the benchmarks. And we can also increase the CPU utilization by around 20 to 30%. And we can also improve the memory bandwidth utilization by 16 to 33%. In summary, we present Rhythm, a deployment controller in Datacenter that maximizes the resource utilization while guarantee LC service tail latency requirement. Any questions?